Today I will quickly give you an overview of my research, of the work I've done at the University of Bonn that culminated with the thesis that I defended in March. So yeah, today we will talk about robotics in horticulture, specifically autonomous harvesting in high-value crops. That means strawberries, sweet peppers, tomatoes, and crops like this. So to give you an overview so that we're all on the same page, this is how today fruit harvesting is done. So you can see there is still a manual work. So it involves people on the field collecting and grasping fruit, making sure that they're not hurting them, and then transport them back to a collection point. So this raised concern on labor shortage, as getting workers is getting harder and harder to find. We have also issues of loss of arable land, which is due to the effect of climate change, which I will not go into detail here, but I just wanted to point this out. So what we see in the future is to go from this human-made harvesting to a more autonomous way where robots can actually harvest fruit for us. So in the image here, you see the facility where I was working on in Australia, where we have this vertical farm with a robot in front of it, which is looking at the scene and detecting fruit and harvesting them. So what we want to achieve is have a harvesting pipeline which is fully autonomous. This can enable large-scale vertical farm as a means to fight the loss of arable land, and we also want it to be sustainable. This also has the advantage that can be implemented close to bigger cities to minimize transportation costs and pollution. So during my thesis, I've done the different contributions, starting from the adaptation of computer vision algorithms to different scenarios. I've done estimation of 3D shapes of fruits and plants. The association of these shapes then has been developed also in a spatiotemporal way to understand how a plant grows over time. And finally, the robotic harvesting pipeline. So in the interest of time, today I will mainly talk about the shape completion of fruit and how we can integrate this into a robotic harvesting scenario. So this is basically one of the most common cycle in robotics. So it's a pretty standard sense, think, and act. This means that first we have to sense the environment. Specifically, we want to understand where the fruits are, how big they are. And we want to have a robot think about what's the best way to approach this fruit. And finally, we can perform the acting part so that we can actually go there and grasp the fruit. So today I want to quickly go through this cycle, showing how my thesis contribute to this. So before diving into the technical part, I want to point out the state-of-the-art review on selective robotic harvesting done by the Wageningen University in 2020, where they mainly pointed out two different challenges for robotic harvesting. So the first thing is that robot needs to deal with incomplete information, which is mainly due to occlusion, which are common in agricultural environments due to the clutter nature. So, and the second one is the lack of a clear paradigm to actually design end effector. And by this I mean that to harvest different fruit, you often see different tools to grasp the fruit, and I will show you some example later. Like these two challenges are slowing down the development in this sector because again there is no real standard solution on how to approach this. So this is one of the robots that was developed during PhenoRob, and it's collecting data in a greenhouse at CKA. And here you start to see the problem of dealing with this incomplete information, because you see that the robot has basically only one point of view to capture the data, and this leads to occlusion, to noisy data, and things like this. The other problem is the lack of standards in the design of the end effector. Here we see 4 different harvesting robots. Here on top, we have a harvesting of a sweet pepper, where we see that the robot is trying to cut the peduncle and then is collecting the sweet pepper from the bottom. Another example here where we actually want to aim for the peduncle on top of the strawberry and cut it. This has the difference that is grabbing, like harvesting and then holding the fruit at the same time. But we also have different approaches. For example, here there is a soft gripper inside the robot, which is holding the fruit so that the robot can pull it apart. And notice here that the robot has to go from the bottom rather than from the top. Last example here is a apple harvesting robot, and here they're basically it's kind of a vacuum cleaner to get the apples. So these are 4 examples. There are many more, but you can start to see that there are really different way of approaching the fruit, and this is what was pointed out in the review I was mentioning before. Okay, so I will start by the sense part, specifically how we can use this incomplete information and how to get better understanding of how our fruit looks like. So the first thing that we want to do is to develop a perception system which is robust to occlusion. So our goal is to, first of all, learn how a general fruit look like so that we can use this information to actually complete shapes when they are incompleted or to filter out some noise. So this is really important, again, to have our robot understanding the environment. So we go from a point cloud, which is partial and noisy on the left, and after this first part, we'll see how we can actually get this 3D mesh that you see here with these lines, which is a representation of the same fruit, but in a more complete way. So our first observation here was that we as humans know how a fruit look like, and we want to have this kind of knowledge also in our robot. So we want to exploit high precision 3D point cloud to learn this general fruit representation. And what I mean by high precision 3D point cloud is something like the following. So we have this non-actuated measuring arm with a 2D LiDAR on top. And we collect a bunch of point clouds where we manually place sweet peppers in front of it. So this is really accurate and really gave us an opportunity to evaluate our approaches, but also to learn how a fruit look like. This is our data collection scenario. Again, this is done in collaboration with the geodesy group. And you see that this is involves a lot of manual work because we had to go manually around the fruit for each of them to collect as many points as possible. So this is what we obtain in the end. So these are just 3 examples, but you can see that we really have highly precise and detailed 3D representation of fruits. And this, when you compare to their corresponding data coming from an RGB sensor, the difference is really striking, right? So we want to have, from the RGBD, we want to go back to the LiDAR with our learning approaches. Now, of course, to work with this in the same pipeline, we have to do a registration pipeline, but I will not go into the details here. Okay, so how do we learn, and what do I mean by general fruit representation? So in computer vision, this is typically defined as a latent space, which is a high dimensional space that encode some relevant information about the task. So here, what I'm trying to show you is that different points in this latent space encode different shape information. So if we go from the dark blue here, we see a sweet pepper which is long and thin, and as we move on the other side of this latent space, we want to obtain sweet peppers which are more round. So this is what we want to achieve using the data that I've shown before and some learning strategies that I'm going to discuss next. So we will use deep neural network for this, and these are standard for various perception tasks. You've probably seen them already, object detection, semantic segmentation, things like this. And these networks are typically trained in an end-to-end manner so that the whole pipeline is treated as a whole block. This is not what we're going to do for several reasons. The first thing that is we want to have different data, different images and point clouds coming in at the same time. So our architecture looks something like this. We have our image, which is our input on the left. This is an example from the lab, but here is where the data from the robot comes in. And then you have your neural network, which is typically composed by an encoder, which has the goal of extracting information and defining this latent space I was talking about. And once we have this latent space, we want to decode this information to obtain the desired output. So the main thing here is that we are training in two different steps. We're first training one part and then the other. And this is mainly due to the fact that we want to use the high precision point cloud in here as well, and not just relying on the RGBD images. So we start by training our decoder. And for this, we use, again, this 3D point cloud that were collected before, plus one latent vector, which is random initialized. And we also want to optimize this latent vector during training so that at the end, we can obtain this nice smooth latent vector, latent shape that I was showing before. So we take these points, we pass into the decoder, and then we want to obtain a signed distance field. A signed distance field is basically, so for each point, we obtain a value, which indicates how far we are to the closest surface. And so this allows us to obtain 3D meshes, which is what we want at the end for our robot. So to train this, we start with a reconstruction loss. So we simply compute the output with the ground truth value, but we also want to include some regularization term on the latent space. And again, this is important because we want to have control over our latent space, but we also need it because later on we will plug in the encoder, and so we need to know how this latent space evolves during the training of the decoder. Okay, so our end goal is to really have noisy input and noisy and partial input and complete and noiseless output. But so far we've just seen how to work with complete input as well. So we now focus on the encoder training so that we can actually exploit this prior information which is already into the decoder and use that to complete RGBD images. So at this stage, we're just training the encoder. So we keep the decoder trained on the high precision data. So we're not updating this part of the network at this stage. We're just updating the encoder. And here we use the RGBD input rather than the point cloud. This is a really important difference because this is the data that we will get from the sensor on our robots. We define different loss functions. The first two are exactly the same that we've seen before. But we also introduce a different loss function, which is a contrastive loss that I want to go a bit more in detail so that we know what we're talking about. So typically what you see is that we'll have different viewpoint of the same fruit, which is indicated here in blue. So the blue box represents the same fruit, but seen from different viewpoints. And then you have a different, a second sweet pepper, which is seen here in red. So when our latent space is without this with loss, what we can end up with is that in this latent space, which is, again, we are not have so much control over it. It can be that this center image is actually projected closer to the red one. And this is not what we want, right? So we want, after training, to have these two images going closer together because they are representing the same fruit. So we want to have the same shape as output. And we want to have this difference in the latent space. So we want that images from different fruits are spatially separated. This will help in the reconstruction phase. So we train this model and we compare it with different baselines. So here we have the chamfer distance, which measure how precise our 3D reconstruction are. And you see that we are comparable with the slightly better than the baselines. But the nice news for us is that we are much faster. So we can go we can have one estimate in 4 milliseconds, and this means that we can run our algorithms online on a robot. This was a really important news for us because it means that we can actually deploy our system online. So here I want to just give you some qualitative understanding of what we obtain. So you see here the predicted mesh compared to the input, and you see that the input is noisy and is partial, but we still managed to get a 3D shape which looks reasonable in terms of sweet pepper shapes. Again, some example here. In the middle, you see the prediction. On the left and on the right, you have input and ground truth. And in the middle also, we have colors which indicate the distance to the ground truth in terms of 3D accuracy. You see that most of the errors come from the top and the bottom of the prediction, which is something we were expecting given our data collection pipeline. But the nice thing is that even when we have really just a few points here on the left, we can still manage to get a shape that looks like a sweet pepper, or at least an approximation of it. We run the same experiments on strawberries to test that our model can also work in this scenario. And again, you can see similar patterns. So error comes from the bottom and the top mostly, but we can still manage to estimate our 3D fruits. Okay, so here this is the first part that I want to talk about, and the main contributions lie in learning this prior over fruit shape. This is done again using high precision point cloud, and thanks to this prior, we're actually able to estimate the complete 3D shape from partial data, and we can run all of this with a really high inference time, so that we can go from a partial data to a complete mesh. Okay, so we can now move to the next part, which is basically thinking about how to approach the fruit once we have this 3D shape, and finally perform the harvesting operation. And to be clear, the main contribution here mainly lie on the thinking side. As for performing harvesting, we rely on state-of-the-art tools in the robotics community. So here I want to bring back these two considerations again, and then especially one thing here to notice is that we haven't talked about this lack of standards. Here I want to argue that different fruits will have different requirements in terms of how we harvest them, but we can still define a vision pipeline that can be easily adaptable to these different and effective designs. So again, just to recap, here we had two examples where we want to go harvest the fruit from the top, one where we go from the bottom, and one where we go from the side. My goal here was to have a vision pipeline that can be used independently of this and effective design that can be used in each of these scenarios. So how do we do that? How do we improve robotic harvesting with this novel perception system? And this is work that I've done in Australia during my research stay that was funded through PhenoRob, for which I'm really grateful. So yeah, the goal here was develop a harvesting pipeline robust to occlusion, and we want to run the same pipeline independently of the end effective design. Again, those are two goals that we want to achieve to push this research field forward. So this is an overview of our pipeline. So we start from our robot looking at the vertical farm. We are segmenting fruits, and this is also done with standard tools. And then we can go on, estimate this 3D shape, and start to understand how do we actually approach the fruit. So let's start by looking at the working environment. Again, this is a vertical farm that was developed in Australia. So you see here they were growing strawberries on the left and tomatoes more on the right. We have our 6 degrees of freedom robotic arm, where we have an RGBD camera mounted on top, plus a gripper to harvest the fruit. And then this robot can move up and down and sideways thanks to a custom-made gantry system. We also designed two different end effectors. One is very similar to the one that you see in the video. It's designed to cut peduncle in strawberries. So we want to cut the peduncle there and then hold the fruit. And the other one is made for harvesting tomatoes. where it's much harder to cut peduncles because of the clutter. So we decide to actually grip the tomato from the side and then just pull it apart. And again, if you notice here these three arrows, which represent the coordinate system that we want to achieve when harvesting the robot, you see that one is on the top, close to the peduncle, and the other is at the center of the fruit, because that will be our target point for this end effector. Okay, so again, to find fruits in the working environment, we rely on standard perception tool. So this is just an instant segmentation network. There are many examples available right now, so I will not go into details here. And this is the 3D shape estimation that we've seen previously, right? So given one detection, we obtain the point cloud thanks to the depth channel of our sensor, and we can now estimate its complete shape. But how we actually exploit this 3D shape was the research question here. Here I also want to introduce the work from my colleague Yue at the University of Bonn, where he had this really nice feature from my approach, where together with a complete shape, you also estimate 6-degree freedom pose of the fruit, so that we know its size, we know how big the fruits are, but we also know how it is oriented in space. And this is really important, because if we want to cut the peduncle, we need to know where the peduncle is. And by design, we define this peduncle to be on the z-axis, which is indicated here with blue arrows. Okay, so we start by noting that fruits are almost symmetrical. This means that once we identify where the peduncle is, we can approach this point from different direction. And this is really something that we want to exploit, because some directions are better than other. It means that some direction may be with more free space around them. Some others may be closer to obstacle or to the vertical farm structure, and so we want to avoid them. So we can define this in a more formal way by defining a maximization problem. Tau C here is the set of possible poses from which we can grasp the fruit, and we want to find the T among this set and maximize some utility function, right? So this utility function can be defined in multiple ways. We start by maximizing space around the robot, and we also want to maximize the distance to the robot workspace limit. And this is a concept that may sound weird, but we are very familiar with it. Like when we, as human, handle objects, we never reach them with a arm fully stretched, because that's not comfortable for us, and we're actually limiting our capacity to move. And so this is exactly what we want to achieve here. So we want to have our robot to reach the fruit in a place where the robot is comfortable with, so that we can move it around in all possible directions. There is a mathematical formulation from this that depends on the robot joint configuration, but I will not discuss this now. So this is our scenario, right? So we have our robot here, we have our estimate, and we can now get our T star, which is our optimized, the pose that we say that's the best one among the ones that are available. And based on this, we can define a path to move our robot from the start position to the harvesting part. Again, these are all standard tools that we use. So we start with RRT, which stands for randomly for random tree, so that we can rapidly explore random tree. So it's exploring the environment, the free space environment around it, and finding a path to the goal. And then we need to rely on a standard inverse kinematic solver to go for executing this path. I want to show you some results here. So this is a collage of 4 different experiments. Of course, we've done many more, but I want to show that here you see that the robot is trying to reach for this comfortable position. It's not just going straight to the fruit, because that's the pose that we found to be more easier for the robot to reach, or the one that maximizes this distance to the workspace limit. So we've done, again, different experiments also on tomatoes. The only difference here means that instead of cutting the peduncle, we're aiming for the center of the fruit. But again, you see the same set of experiment. Again, also here you see that the robot is going for this middle position in its workspace limit. In terms of evaluation, we compare our harvesting pipeline with different approaches, which are relying on shape completion, but also not. And you see here on the right where we compare the success rate of different harvesting experiments. Our approach for both fruits can actually give us much more reliable results. So I want to quickly mention the baseline here. So what I mean by detection here is that we're not relying on any 3D shape completion. We're just detecting the grasping point. And you see here that due to occlusion, in this example, the robot goes not for the peduncle, but for the fruit itself. And this is not really what we want, especially for harvesting strawberries, right? The other example here is where we actually introduce a simple shape completion approach, which is not relying on neural networks. So here, given a 3D point cloud, we are just fitting a simple shape on these points, and you see that especially the orientation estimation of this fruit is wrong, so that the robot is going in a different direction. Okay, so here the contribution of this second part were mostly in improving this robotic harvesting pipeline, exploiting our 3D shape completion work. And the nice thing for us is that we can really use the same vision system and adapt it to different end effector design without the need to implement a whole new perception system. So with this, I show you how we can close this sensing cycle out in this application of robotic harvesting. And when we look back at this consideration in 2020, which is roughly when I started my PhD in Bonn, what we can say now is that we know how to deal with occlusions, especially in fruits. We can estimate 3D shapes of fruits from cluttered environments when only a partial view is present. And we also know how to use this estimate and have different end effector design work independently of their design. They can work on the same perception system. This means that later on the research field can move much faster in the developing a robot and vision system, because we don't have to again implement different system each time. That's it from my side. Thank you for the attention.